Welcome to my talk about our algorithm for threading assignment in large-scale wireless networks mobile simulations. My name is Orestes Manzanilla. I will start the presentation talking about the context of our work and the state of the art. And then I will explain the model and the algorithm proposed, and we'll wrap it up sharing some promising numerical results and our conclusions. What have we done in this project in short? Essentially, we found a new and interesting way to improve multi-threading performance when we are simulating large-scale wireless wireless networks involving mobile devices. It is independent of the wireless technology, the computing architecture, and the mobility patterns of the devices. We found improvements ranging between 36 and 100%, and interestingly, found out that some large-scale aspects are actually good for the method. To give some context, we could ask, why is it interesting parallel computing for this kind of systems? Essentially, it is because we are focused on very large simulation with hundreds of base stations. And why do we need to simulate so large systems? The reason is that to study how the telecom affects geographically distributed applications, we need to simulate the telecom behavior of the city. Investigating this in real life is extremely costly and difficult. This is relevant because in smart cities, more and more Internet of Things devices that connect or will connect tomorrow to wireless infrastructures of smart cities will be competing for the network resources with the traffic produced by normal communication demands in the city. We need to study not only the layer of how the applications work, but also the subjacent layer of the telecom subsystem that allows the elements of the applications to interact within themselves and with the user. To understand the performance problems caused by mobility, let us imagine some regions of a city covered by different base stations. Let us imagine a bus that is being served by the base station 1, for example, and eventually will be moving towards a region that is served by another one, base station 2, for example. When both base stations agree and transfer the service from one to another, we call this phenomenon, this event, as a handover. When we simulate the telecom systems using parallel computing, it is natural to assign each computing unit a subset of the regions. We will have two types of situations when handovers take place. First, the first possibility is that the new base station is in the same thread or the same computing unit as the original base station that was serving the bus in the first place. This is good news for us because the computing units can keep working independently in parallel. The second possibility is less good. It is when the new base station that will serve the bus is being simulated in a different computing unit. Threads or computing units in general have to stop then, synchronize, update the states, and transfer the object that represents the bus from one to another. After that is done, the parallel computing can start again. The problem is that the parallel computing had to stop, and if that happens frequently, it will take away partially the benefits of doing parallel computing in the first place. We call these stopping events synchronization points. One way to define our problem is that there are three factors that increase the probability of having handovers. First, having more base stations. Second, having more UEs. And third, having long simulations, essentially. The first two tend to increase in smart cities. The third one is necessary as the performance for applications that are geographically distributed is relevant in a scale that is usually in minutes or hours. More handovers, on the other hand, means higher probability of having synchronization points, which we want to avoid because they hinder the computational performance. What we found interesting is that we can affect the occurrence of synchronization points by considering in a smart way the trajectories that the devices that move and are connected to the network when we assign the regions to the computing units. In our proposal specifically, we need two things for our proposal approach to be feasible. First, we need to be able to estimate the signal strength received from base stations across the space in the city. Second, we need to be able to assume that the mobile devices' trajectories are independent of what happens at the telecom level. Having both things, what we do is we pre-process trajectories and take note of when handovers take place between base stations. This is something that has to be done only once, unless trajectories for base stations or the propagation changes, of course. Our proposed algorithm takes this list of events and uses it to smartly assign base stations to threads or computing units, with the objective of delaying as much as possible the need for a new synchronization point. Once our algorithm is executed, we have then a prescription of how to split computation when simulating large-scale telecom subsystems. That is the moment when the proper intensive parallel computing simulation of the telecommunications takes place, taking into account the whole city. If received signal strength across the space does not change, nor do the trajectories, our algorithm can be run only once and serve for many telecom simulations in the future. So there are three big research questions that motivated this work and also how we design our experiments. First, how to distribute, what's the best way to distribute the work among parallel computing units to make the simulation faster? Second, is this worth the effort? And what we mean is, does the improvement justify this extra work of preprocessing and doing our algorithm? And finally, under which conditions does our algorithm work better? Conditions meaning characteristics of the simulation, of course. Regarding the most, now talking about the state of the art, regarding the most relevant aspects of the papers that we revised, that we checked, we see that there are many that, of course, do parallel computing to simulate cellular networks. Some of them, like StreamNet, incorporate mobility. However, it seems that the overhead that includes the rolling back is not appropriate for the dimensionality of the problems that we are focused on, with hundreds or more base stations. Others not only split the computing work geographically, but also by channels, the channels of the transmission. But these are not well suited for large-scale cases with mobility. We found also works specifically in 4G and LTE, which are the more frequent cellular infrastructures right now. However, mobility and handovers are not dealt with using parallelism. So what do we do different from previous works is that we focus on dealing in an efficient way with mobility and handovers using parallelism. And we came up with a strategy that happens to not be dependent on cellular technology or the mobility models used for the devices that are connected to the network, and the architecture at hand for the parallel computing, as long as the architecture suits itself for telecom simulations, of course. Now, how did we model the city wireless infrastructure for our experiments? It's rather simple. It's a square fictional city with base stations that are the black antennas in the figure, and that are distributed in some way. In the figure, we show them irregularly placed, randomly specifically, but we also made examples under the same, keeping all the other conditions constant, where they are placed in a square lattice. And for simplicity, we consider that the signal strength is proportional to the distance of the base stations, because there was no justification to do this in a more complex way for the goals of our research. We divided the city in squares, in a square grid, as can be shown as can be seen in the figure. And the black dots that are in the center of the small squares represent we call them grid points. For each grid point, we do some work. We pre-compute what we call a priority list assigned to the grid point, and it has the list of the n closest base stations ordered from the closest to the farthest one. This way, depending on the location that a particular device or the cars have in the city, they inherit the priority list of the closest grid point to where they are. In our implementation, handovers take place then when a bus, for example, one of the blue buses, moves so it gets closer to a new grid point, and this new grid point does not have the base station that is serving the bus. So it doesn't have that antenna or that base station in the priority list. What will happen now is that it will connect to the best base station in the list of this new grid point. The story about the mobile UEs, which were our blue cars and buses in the previous figure, is that they move at a constant speed and a constant direction as well. And these are chosen randomly. The intuition, now speaking about the proposed algorithm, the intuition we use lies in considering that when the simulation starts, the base stations are considered disconnected trees in a forest. So this is a graph, in particular a forest, and it starts with each one being a single node, but also a single tree. In this example, at time 0, we see 6 disconnected trees corresponding to the 6 base stations. As we go over the table of the handover events that we get from the preprocessing, we see that at time t1, 2 handovers take place, each between a different pair of base stations. Our abstraction consists on thinking that when these handovers take place, they create a link between the origin and the destination base stations. In terms of graphs or trees, we would say that the trees have merged. As a result, at T1, we have gone from 6 to 4 disconnected trees. Going further down the list of the handover events, another one takes place, merging one of our 2 node trees from T1, with another base station. Because of this merging, we went now from 4 to 3 disconnected trees in the forest. What is interesting is to notice that if we choose to assign the base stations that belong to each disconnected tree to a computing unit, we would be able to run the telecom simulation up until not only T2, but also a little more time until a new handover takes place and merges again some trees, without needing to have a synchronization point. Essentially because we have the guarantee that there are no handovers happening between the disconnected trees. In a big city with many base stations, if we go for long enough through the handover events, the trees will merge until there are as many disconnected trees as the number of threads that the user wants to use for parallel computing. And this is the eureka moment. The belonging of the base stations to the disconnected trees is the prescription of how to assign them to different threads. Let's see how good this idea actually is. In this figure, the horizontal axis is the simulation time. The vertical axis is the count of the disconnected trees in our forest. Each time the blue line or the green dashed dotted line ceases falling down and jumps up, it means that there is a synchronization point, essentially. So we start by this reset means that the base stations are considered single node trees again. In fact, this synchronization happens each time the number of disconnected graphs gets equal to 15 in this case, which was the required number of threads for the example. It's like a bouncing. In blue, we see the evolution of the number of trees when the base stations are assigned to threads in a smart way, and by that we mean our proposed method. In green, we see the case when they are assigned randomly, but in a balanced way across the computing units. We can see that after 2 hours, we have had 7 synchronization points with just a balanced assignment, but random balanced assignment, and 1 synchronization point in the scenario where we use our method. We see that this pattern where we have less synchronization points using our method is repeated across all of our experiments. Long story short, the smallest synchronization points reduction was 31.6%. And our best cases had a reduction of 100%, and that means we got rid of all the synchronization points in those cases. Fortunately, we found that very promisingly, this happened in 65.2% of the experiments. And by that I mean across all the sweep across combinations of experimental conditions. 65.2% of the time, the reduction was of 100%. Now, what things worked in helping our method get better reductions? First, we noticed that the method was better or worked in a more effective way when the base stations were placed in a square lattice instead of randomly placed. Secondly, we found that having a finer granularity, which is usually a bad thing, was actually good for us. And third, having more base stations was actually a good thing. The things that deteriorated the performance of our method were having more user equipments that are moving, of course, because they produce then, of course, more handovers, and also requiring more threads. To wrap up, we can say about our work in this method to reduce computational overhead in parallel computing, simulating large-scale wireless networks with mobility, that first, it requires the ability to predict handover events. Secondly, that we have come with a heuristic that is general enough to be independent of the telecom technology, the parallel computing architecture, and the mobility patterns considered. Third, that it seems to be worth it, as most of our 4-hour simulations had a performance improvement of 100%, and the worst cases had improvement of higher than 36%. Lastly, we saw that some large-scale characteristics were actually good for the method. We leave here for you some references related to our comments on the state of the art. And now it's the turn for you. May you have some questions about our work.